So welcome back to the next lesson when it comes to electrostatics. So in the previous lesson we learnt about the electric field lines and also the electric force associated with these field lines, of course being tangential to the field lines, and also how the electric fields interacted with positive and negative charges. Okay, so we're going to go now into that with more detail and a few equations which you need to know. Okay, so the electric field lines start from a positive charge and stop with negative charge. So the direction of the field goes from positive to negative. They never touch or cross, and they are perpendicular to the surface of conductors. Okay, so if you have a conductor, if you say a piece of metal, okay, then they're going to be perpendicular, okay, at right angles, as we can illustrate by the diagram. Of course, assuming that is positive. And on this surface, obviously, again, perpendicular. Okay. So, in terms of electric field strength, the equation you have to know is E equals F divided by Q. So the electric field strength E is the force experienced per unit or per coulomb of charge, because the unit of charge is the coulomb. An electric field strength is a vector, okay, so it has a direction as well as a size, and its direction is the same as the direction of the force experienced by that small positive charge Q. And the units are newtons per coulomb, or NC to the minus 1. I can do this. Okay, so here's a few examples using this equation. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. So the field strength is given for this particular question at 1000 newtons per coulomb. What is the force on 1 coulomb of charge, or even on an electron? So force equals E times Q from the equation, which is going to be 1000 times 1 for the first example where the charge is 1 coulomb. So that gives a force of 1000 newtons, rather massive. Whereas the charge of an electron is a lot smaller, so the force again equals E times Q, 1000, the field strength, times 1.6 times 10 to the negative 19, which is the charge on an individual electron, which gives an overall force of 1.6 times 10 to the negative 19 newtons. So you can see that because the electron's charge is small, the force exerted is a lot smaller. So the second question asked, a charged sphere is placed in a field of strength 3 times 10 to the 4 newtons per coulomb. If it experiences a force of 15 newtons, what is the charge on the sphere? So the only equation we have at the moment is force equals E times Q. So you rearrange that to get Q equals force divided by E, which will equal 15, divided by 3 times 10 to the 4, which gives overall charge of the sphere of 5 times 10 to the negative 4 coulombs. And finally, what is the field strength if an electron experiences a force at 4.8 times 10 to the negative 14 newtons? Again, the only equation we have is E equals F equals E times Q. So if we rearrange that, you get the electrical field strength equal force divided by the charge, which will be 4.8 times 10 to the negative 14, divided by 1.6 times 10 to the negative 19, remembering that's the charge on an electron, giving an overall field strength of 3 times 10 to the 5 newtons per coulomb. Okay, so another concept you have to learn about is electrical potential energy, and I like to use the analogy with gravitational potential energy. Okay, so here we have a mass, m, falling in a uniform gravitational field, be it on planet Earth or Mars, okay, and that force is going to be equal to mg, the mass times the acceleration due to gravity. So the work done to raise a mass against the Earth's gravitational field, okay, so we're looking to move that mass, that will require a certain force, and will be a change in the gravitational potential energy. And there'll be work being done because it'll be force times distance, okay? So there's going to be a certain distance. So the work being done equals force times distance, or mgh, the actual gravitational potential energy. Whereas in terms of electrical potential energy, we have the force equaling E times Q from our previous slide, and a certain distance that it's being moved up. Okay, so work done to move the charge against the electric field will be again force times distance, but remembering force equals EQ, and you've got this certain distance. So just like MGH, we have another equation which will be associated with work, which is going to be work equals EQD, and that's going to be the change in potential energy, EP. And we also call this the voltage, but that's for later. Okay, let's move on. So here's an example. A charge of 2 times 10 to the negative 6 coulombs is pushed 20 centimeters against an electrical field of strength 400 newtons per coulomb. And the gain, what is the gain of electrical potential energy? Okay, so we've got some numbers here. That's going to be your Q. Just delete that rather messy Q. That's going to be your Q, right? That's going to be your distance. And remember to convert to meters. And you've got an electrical field strength of E. Okay, so delta EP, the change in potential energy, is going to be work, which will force times distance, which is E times Q times D, which is 2 times 10 to the 6 times 400 times 0.2, remembering to convert that into meters. So the answer is 1.6 times 10 to the negative 4 joules, and that's our answer. Okay, so let's move on to a idea of electrical potential difference. Now remember, I did mention voltage. Okay, just to end the lesson, I'm now going to link the potential energy to voltage. Okay, the electrical potential energy change per unit charge is called the electrical potential difference. So you may have heard that previously. Okay, but you're very familiar probably with the idea of voltage. So the unit of the volt is 1 joule per coulomb. So it's the amount of energy per charge. So a charge of 1 coulomb through a potential difference of 1 volt gains 1 joule of potential energy. Okay, so voltage is essentially the amount of potential energy divided by the charge. So it's the amount of potential energy per charge. So as an example, a 1.5 volt battery gives a 1.5 joules of electrical energy to each coulomb. Okay, so 1 C of charge it delivers to a circuit. And that should be enough for today's lesson.